really wrapped up in the interesting structures of line defects, pi1 defects. We didn't get to two other interesting cases that showed up quite a bit this last week. So, okay, so we're trying to explore the topology of the space of ground states. We looked at the simplest thing, whether it's connected, and then we looked at whether it's simply connected. And simply connected, we probed by trying to lasso the space with loops. In all these kinds of geometry problems, you use different probes, just like in physics, forcing the system, sampling the system. You use different probes to see what it's made of. So there's a couple of more probes we can use, actually a lot more, but only two that turn out to be interesting. We can look at, so we have this space of ground states. We can look at the general rich space. We can look at whether it has two-dimensional structures in it. Okay? So we can look at, the simplest one is S2, the two-sphere. We can look at maps from the two-sphere into M. So here we're delving into the space, not taking loops, but taking a big sphere. And we're asking whether we can contract that down to something trivial, to a point with no structure. So this, the space of basically inequivalent, topologically inequivalent maps from two-sphere into M, looking at nested two-dimensional structures in here, is pi2. So this is pi2. It's basically a set of inequivalent topologically inequivalent maps from S2 into M. Now, you have this big two-sphere, like this balloon, and you deflate the balloon step by step, coming all the way down. It's continuous, everything looks fine, There's nothing singular, nothing special inside the balloon. We can contract it all the way down. So if that's not true, if there are topologically non-trivial two spheres inside the space, then just like our argument before, there's some point, there's some defective point inside the balloon. So if this is non-trivial, this implies point defects. So you've seen all of these. For both, so this is a case for both magnetism and the liquid crystal, our main examples, have defects. Remember, for magnetism, the order parameter space was S2. So this is simply a two-dimensional analog of the winding number, pi1 for the circle. You can wrap a two-sphere an integer number of times on a two-sphere. So pi2 S2 is Z. So these are configurations. These are the point defects are monopoles. So this is magnetic field, say, going radially outward in 3 dimensions. We had these as vortices, or in biophysics they're called asters. In 2D, here this 3D example, it's called hedgehog. So, radially going out everywhere from a point. Down here is your defect. For the liquid crystal, this has in it, M was this RP2, which is S2 mod Z2. It has this S2 in it. So this also has a Z. This is a little bit richer because there's some funny things having to do with how the line defects interact with the point defects. Turns out, because of this Z2, you take a monopole charge in the liquid crystal case and pass it around a string. You can turn it into a monopole charge minus N and have it annihilate itself. But that will take us a little bit too much time to go into. Finally, there's something more bizarre which Smollett exploited quite a bit. There are non-trivial maps from the 3 sphere, going in higher dimensions now, down to 2 sphere. You can have non-trivial 3 spheres inside this order parameter space for both liquid crystals and magnetism associated with S2. We have a function like this. So now we're looking at pi 3 of S2. There are 2 ways to describe this topology. This turns out to be Z also. So this is beautiful. Beautiful result. We won't prove anything, but it'll indicate the nature of the topological invariant. First of all, how do you get S3? Okay. That's very natural for this magnetism case or for liquid crystals. Let's take a vector field just in bulk 3 dimensions. So this is what we would call R. Take a vector field that's living in R3 and let's take it and have unit magnitude. So this means the components, n1 squared plus n2 squared plus n3 squared is 1. So this maps it onto S2. So this gives a map from R3 to S2. It's just a unit, fancy way of saying you have a unit vector field on the space. And then let's, at infinity, let's fix the boundary conditions. So the field n as x goes to infinity is some fixed vector field. This means as you roam out to the boundaries of your space, you go to the same point always on S2, this fixed one. This means all points at infinity are the same. So this means you take your space, think of a 2-dimensional space, like this, 2-dimensional space, which is the line ball pattern, and then you identify all the edges are the same. If all the edges are the same, you can wrap that up into a point, add that point to your space, and you have, identify, you have a sphere. Instead of in this case, you have a 1-dimensional sphere, the boundary of this thing. Instead of R3. So with this, if you have this boundary condition, R3 becomes S3. All the points of infinity are the same, no boundary. So this gives you S3 next to S2. So that's very easy to get. Now what about the invariant? The invariant has the following form. So we're mapping from a 3-dimensional space to a 2-dimensional space. What we do is S2, here's S3. This involves collapse one whole dimension in order to go from 3 to 2 dimensions. So if let's pick 2 points over here on the target manifold. Let's put X and Y here. And let's pull this back to S3. What's that going to produce over here? What dimension object?
Janice, if you don't respond, you lose the bottle.
That's right. I'm sure some text. You're going to have text. The prices. Negative prices. Michael.
Me.
Lisa. Remember, we're going to lose a dimension. We're going to make 3 dimensions down to 2. So here I'm starting with, so 3 goes to 2. Here I'm starting with 0 point. Yes. It's going to be a 1-dimensional object. We're dealing with stuff that begins and ends also at the same point. So the 1-dimensional object is going to be a loop, piece of DNA, if you want. And then we pull, so this will be, say, gamma 1. And we pull this one back, makes a loop. It might be linked. Not quite supercoiling, but similar. Linking. This is gamma 2. So we compute the linking number, which appeared in Jean-Francois's lectures and other lectures, of gamma 1 and gamma 2. Then you have some more, yeah.
Do you also get knots in this case?
Yes, I mean there. Yes, this is a knot.
Not for your link.
Yeah. I mean, if you took 3. Anyway, this is a knot. Yeah. Then you have some work to do. If this varied with your choice of x and y, it wouldn't be useful. But you can show this linking number doesn't depend on the choice of x and y. If you take any two, pull them back, compute the linking number of these two curves, you always get the same. So this, and they link an integer number of times. You have to count these links. If it goes over as a +1, if it goes under as a -1, and so on. You have to count them the right way. This is the topological invariant, known as the Hop number. And you have to prove that you can actually construct this non-zero. So that's how it comes about. Now, just a piece of cultural history to show some of the universality of physics and mathematics, and maybe indirectly finance. So we had this vector field, or if we identify with this inversion, the perspective or direct duct, if we identify with its inverse, we had this n. From this n, we can construct an object that looks like the field strength in electromagnetism. And Urosh wrote down this expression in this form, actually. So we can construct something. So remember, field strength in electromagnetism is the curl of the vector potential. If any of you, maybe a few of you have studied forms, this is the exterior derivative of the one form A, the vector potential. An n form is something you can integrate on an n-dimensional space. It couples to area elements, which are cross products, so they could be antisymmetric tensors. Yeah, it's a second rank antisymmetric tensor. Here you can construct this Fij in the following way: epsilon ijk n dot djn cross dkn. So this is Fi. I'll write it this way. I'm taking, if you can take epsilon ijk and take what's called the, you take Fij and take what's called the dual of that, you get a thing with one index. So epsilon take this and you multiply epsilon I j k. You get something like k. Just take this expression. This object here is the f, the antisymmetric tensor, and then I'm going to take it multiplied with epsilon I j k. And then this linking number is equivalently 1 over 8 pi squared times the integral of f dot a over the space. This is over the 3 sphere, and a is simply the curl of a, in this case 2f. So from f, defined like this, we get a by solving this. Curl of a has to be 2f, and we write this f dot a. This is something that can be integrated over the 3-dimensional 3-sphere. So these two, so that's quite a bit of work. These two are the same. That's the one we know. Now, this object, actually in this, written in terms of this thing here, this object in electromagnetism, this is actually F wedge A.
Sorry, I have a question.
Yes.
So you just called this H the winding number. Do you mean linking number, or is there some sort of relationship between the two?
Hopf number, sorry. This is the Hopf invariant, it's an integer. Here it's a linking number, and here's the more general expression for it. Yeah, I shouldn't call it winding number. Do that because it's an integer. Yeah. But it's wrapping 3 spheres on 2 spheres. So this is the Hopf invariant. There's a similar object in electromagnetism, 3-dimensional electromagnetism. You know how to construct this in electromagnetism. You know how to construct this. And if you integrate this object is called Chern-Simons. There's a lot of beautiful results in field theory. And Jim Simons is a mathematician who did a lot of beautiful work in geometry, Berkeley, and did a lot of work on cryptology, and funded a company called Renaissance Technologies that managed hedge funds. So they started off with something like, I don't know, $15 million, and Jim Simons' net worth now is $12.5 billion. So they have a foundation that does a lot of work supporting science, mathematics, and physics, postdocs, research fellowships, prizes, and very good web pages on science. Really well worth reading. So this thing here is simply a kind of a liquid crystal, if you want, analog, those linking numbers that Ivan was exploiting, of this Chern-Simons form. The thing that I like about the liquid crystal case, so we saw but then all the higher homotopies of S2 vanish. So we saw for liquid crystals, we had, so these are the things we could look at, pi 0, pi 1, pi 2, pi 3. This simple kind of start, by starting with not with point-like atoms, but with asymmetric molecules, we got here, this was trivial, but this one is non-trivial Z2, this one was Z, this one was Z, this gave line defects, so loops, destination loops, this gave point defects, monopoles, or asters, or 3D vortices, and so on. And this gave Hopf, sometimes called texture. So there are simple, beautiful liquid crystals in your displays and so on. Simple generalization, asymmetric molecules. You got 3 of the 4 and the 3 richest class topological defects in that one system. So if you want to illustrate these ideas, which I've been trying to do and you've been seeing in lots of context, liquid crystals are the way to go. Incredibly rich. Okay, that's all I want to say to wrap that up, because next week at James I'll talk about something else. Any questions? Yes?
So in your story about Simon's, I couldn't quite follow. And was he using this mathematics for finance?
No. This was his work on geometry. And then he worked on pattern recognition through cryptology. So he worked for Institute for Defects Analysis. And I think as part of this pattern recognition stuff, he thought about the mathematics of finance. I don't know the nature of his work in finance mathematics. That came later. Yes?
So when you were drawing in the middle board here, where you had the 3 space, the x and y points, when you go to the 2 space, they're necessarily linked because they're in the same space as the...
No, they're not necessarily linked. So, okay, so if we take the trivial map, there'll be no linking. So this is S2, right?
Oh, okay.
This is S3. So these can be linked an integer number of times, including 0, which would be like the unknown. So that would be the topologically trivial class. If they link once, that would be winding number 1. If they link twice, that would be Hopf invariant 2. Is that the question?
So what determines whether or not they're linking and how much?
Okay. So remember, okay. Good question. Remember, we're classifying. So any one map will be 1. So all we're doing here is, so I'll only give a vague answer here. All we're doing is classifying all the possibilities. So this will be analogous to this case. Simple winding number case, S1 to S1. We can wind 0 times, the map like that. We can wind once, so the map sort of goes around, might come back, but it's deformable to something wrapping around once, and so on. So we have to compute basically f of 2 pi minus f of 0. So all the homotopy tells you is that there exist maps. For any given map, the winding number is going to be one of these integers. So similarly for the Hopf case, there's a topologically, the maps can all be divided into classes, and each class will have an integer Hopf invariant, including 0. So you have to, for a given map, you have to find out which class it's in by computing that linking number. Does that answer? Yeah. So a priori can be anything, just classifying the cases, and then to exploit, to have a non-trivial defect, you have to pick something from the right class. So the actual computations can be tricky, much trickier here. You have to compute that integral, which is hard. You have derivatives here, then a curl, and then dot it into this, and then to integrate that over. What's nice is the abstract theorems tell you what the homotopy is without doing those integrals. That's the power of it. So Whitehead gave this expression for H, showed that it's in this class that gives you an integer without explicit computation. So that requires a little bit of little bit more knowledge about the topology involved here. It involves something called homology, which gives you a more local picture of the structure of the matter. to exploiting abstract results to show that defects exist. Finding them, exploiting them, identifying them in physical situations. That's the way you go. All those complicated pictures, Ivan, Urosh, and so on were showing. That's work, that's not trivial. But at least you have a solid foundation, you know they exist. You know it has to be in one class or another. Prove something is an integer is pretty cool, for example. Who would guess that this thing here? What is it? I mean, first you have to solve this equation, which is non-local. A is 1 over the derivative of f. Okay? So this is needs a Green's function. So just to get A is long range because of this solving this equation. So you sort of know how to do that. Electromagnetism, usually you're given A and you compute F. Here you've got F. You have to get A. And then do this integral F, dot it into A. And then divide by 8 pi squared, you get an integer. Miracle. That's the power of the mathematics here. And even if you physically could compute it and got an integer, to show that if you slightly, so now you have the vector field in R3. So I go in and I say, okay, what about this vector field instead? This is a small perturbation. This is a continuous deformation. The theory tells you that winding number doesn't change. That's very powerful. Yeah.
Can you use the blackboard, which is the below one? So the figure which is there, like from from the point to the
loop
dimension here, I think.
Yeah.
So what you call a Hopf number, is that link between the two
Yes.
loops?
Yes.
And the H is it like
H is the linking number.
is the linking numbers like how you get it in general?
What?
I don't understand. Is it
Identically the linking number.
okay?
So under this map, a whole curve goes to one point.
Yeah.
You lose a dimension. And you pull it back, get one curve. Pull this one back, get another curve. They link a certain number of times. That is the invariant.
Okay.
And the invariant means if I slightly perturb the map, it doesn't change. It also means if I choose two different points. Since this is supposed to be a property of F, F doesn't know what points you're pulling back. So if I take two different points, I can also compute this. You have to show it's the same, independent of the points you pull back to get this large non-trivial back.
So I guess if you have a torus knot like the ones Ivan was showing in S3, can you map that onto S2 as a point?
So you want to take, so remind me what you're pointing the torus knot with.
Well, they were like trefoil knots or these more complicated.
Yes.
So a single.
Yes, they have three loops,
It's a single loop,
but winding on itself.
right?
It's different structure.
So you cannot map that onto S2.
Okay. Thank you. Did you have anything you wanted to say? I think we. Okay. So we'll finish.